Welcome to Lab 3, Discovering Net Force from Observed Motion. Force, like any other vector quantity, can be expressed as the sum of two other coplanar vectors. And as part of our discovery of the net force, shown here as a yellow arrow, we will break it down into two components, one parallel to the direction of motion, the red arrow, and the other perpendicular to the direction of motion, the blue arrow. For the system, we have a moving star of known mass. And for the surroundings, we make the assumption that the only object interacting with the star is a black hole of unknown mass. In addition to discovering the net force along with its parallel and perpendicular components, we will also discover the unknown mass of the black hole. Central to this lab is Newton's second law of motion. Newton's second law tells us that when there is a change in the motion of a system, in other words, when the speed or direction of the motion changes, shown here as delta V, there must be a net force not equal to zero acting on this system. The force is the cause, and the motion is the effect. Because momentum equals velocity times mass, another way of looking at Newton's second law of motion, also called the momentum principle, is to say that F net equals delta P over delta T. When delta T is infinitesimally small, we have a derivative. Now, momentum, like any other vector quantity, can be expressed in terms of its magnitude and its direction. This gives us a new way of looking at the derivative of the momentum, as the derivative of a product, the product of the magnitude and direction of the momentum. Applying the product rule, we now have a new way of expressing the momentum principle in terms of cause and effect. So the effect is motion, meaning change in velocity or momentum. With the product rule, we were able to break down the derivative of the momentum with respect to time into two terms. The first term is about the change of the magnitude of the momentum, so it impacts the speed, either a speeding up or a slowing down of the system. If it slows down to zero and then speeds up, it reverses direction, but the direction is still parallel to the direction of the system. The second term is about the change of the direction of the momentum. This impacts the direction or curviness of the trajectory. The cause of motion is a net force not equal to zero. While there is only one net force, this force as a vector can be expressed as the sum of two component vectors, F net parallel and F net perpendicular. The parallel component of the net force impacts the speed. The perpendicular component impacts the curviness. For the computer model, we'll start with what we have. For the observed motion, we have a CSV file of synthesized positional data. This data set has two fields, one for the x component of the star's position and the other for the y component. We will assume the star moves in the xy plane with z equals 0. Each row in the file represents a new star position separated by delta t equals 86,400 seconds, or 1 Earth day. This positional data is read by the Python program and stored into two Python lists, one list for the x component and the other for the y component. The positional data, together with delta t, can be used to calculate velocity. The velocity is calculated for successive star positions inside a while loop. The x and y components of velocity are also stored inside Python lists. Let's recap our computer model by looking at what we have. We have observed motion data stored in Python lists for the xy position coordinates and the xy velocity components. We have the star's mass in kilograms, and we have the black hole's position. The black hole's position is given by a vector quantity, and I renamed the origin variable from the template to black hole to make code easier to read. Now we're ready to turn our attention to what we assume. The only force acting on the star is gravity from the black hole. Here we have a simplified version of Newton's universal law, simplified in that it calculates the magnitude, ignoring direction. We know what all of those values are, except for the black hole's mass. So let's rearrange the equation to solve for the black hole's mass. And here it is. I just said that we have all the values on the right-hand side of the equation that solves for the black hole's mass. Perhaps I should elaborate. The magnitude of Fg is easy. Because we assume that the black hole's gravity is the only force acting on the star, we know that it is simply the magnitude of F net. Distance is a bit more complicated, and like F net, it changes as the star moves. But we know the position of the black hole, and we store the values for the star's position as it moves inside Python lists. G is the universal gravitational constant, and we know the star's mass. Now we get to the most important part of the Python program, where we use the motion data that we already stored in lists to calculate FNet, FNet parallel, and FNet perpendicular. We'll also find the mass of the black hole. This calculation is done inside a while loop. The loop will recalculate the black hole's mass inside each iteration of the loop. Theoretically, this mass will be the same each time through, but the program could introduce small arithmetic errors, hopefully not too significant. For this reason, I have created a Python list called black hole masses to hold these calculated values. Later, I can take an average. When we run the program, we find that the black hole has a mass of about 2.57 times 10 to the 31.